Well, I want to visit with you a little bit more about zero force members and how we do some of the analysis. And remember what we said was examine the joint. Well, let's look at this picture right here. Let's look at this joint right there. You can't really tell anything about zero force members there because these two are coming in at an angle. These two are obviously lined up. So you can't really tell anything about joint F yet. So let's move to joint D. In this case, you have these two members that are lined up. And so by observation, if you examine that joint, any force in this member would cause that joint to move out of place. So by observation, that is going to be a zero force member. Now let's go over here and say that, well, if that member is zero, it basically is as if it doesn't even exist. Well, if it doesn't exist, then you can redraw the picture and it looks like this. And now you can look at joint F again and you say, oh, now these two are lined up, and this one can't possibly have any force or it would move that joint out of place. Therefore, this is also a zero force member. And then, of course, if you look at this joint, you can see that this one is a zero force member. So let's go back to our original picture then. We can say that that one is a zero force member. By virtue of this joint, this one is a zero force member. By virtue of this joint, this one is a zero force member. So that's pretty common, where you have to kind of walk through the picture, start with where something is happening, move to something else, and then, well, this one was kind of a standalone one. All right, well, let's look at this picture here. This one here looks like, if I look at that joint, I can observe that this one is a zero force member. And if I look at this joint right here, you can see that, well, that one's probably, whoa, wait a minute, that one's not a zero force member at all. This one's pushing in like this. These two are lined up, but the only way for this joint to be in equilibrium is for this one to be pushing back. So therefore, EC must be in compression, pushing back toward that. EC is equal to 900 in compression, pushing back. All right, how about these over here? If you look at joint H here, these two look like they could be, well, this one looks like it could be a zero force member, except that these two aren't lined up. And that's kind of breaking the rules. These two have to be exactly lined up in order for this one to be a zero force member. So by observation, this one is not a zero force member. And by the same token, if these two are not lined up, then this one cannot be a zero force member. However, if you look at this joint right here, this one is a zero force member. So let's go ahead and put zero force there. Let's look at one more picture here about collinear members and what we had talked about before. If this 2 kilonewton force is coming in, because these are lined up, the only way for this joint to be in equilibrium is for this one to push back at that same 2 kilonewtons. If that one is 2 kilonewtons, that has to be in compression, meaning pushing toward the joint. And what that means is over here, AB and BC are now concurrent. They are the same because these two have to be the same. If I look at this though, if that's pushing in this way, this one is not going to be concurrent with that. It's not lined up. Therefore, this one is not 2 kilonewtons. It is something else, not equal to 2 kilonewtons. And these two are not equal. AB is not equal to BC. So again, I hope that that makes some sense. Let's look at some more examples here of zero force members. And what I'd like you to do here is pause this video and go through and mark each of the zero force members that you can see in each of these pictures. So pause the video for a few minutes and work with your study partner if you have one, and see if you can identify all the zero force members that you can. Well, here's the solutions. We already did this one, so that one should be familiar to you. I hope all the rest of them make sense as you walk through them. One of them I want to point out is this one right here. I'm going to zoom way in here. And what you can see is by joint, you can't really tell much about these zero force members until you zoom in a little bit. And what I'm going to say is by virtue of joint E, this one is a zero force member. And then if that one is 0, if you look at joint C, this one is 0. And then if this one is 0, look at joint F, and then this one is 0. And then if we look at that one 0 by joint B, this one is 0. So you have 4 zero force members there. None of these you could have understood until you start with that one and then walk all the way through it. On both sides of this, you have concurrent force members here. These are all lined up, so therefore they all have to be the same. These 3 are all lined up, and so these 3 are all the same. These are not the same as those, but they are all equal to each other on this side, all equal to each other on that side. All right. Well, the next thing I want to talk to you about is where you apply the force makes a difference. When we were talking about straightforward beams, then we used a principle called transmissibility, and that still applies when we're trying to understand external reactions. However, you have to be careful with that when we're doing internal forces. All right, so here we have a 900 and a 600. Let's say that we applied the 900 instead over there. We applied it here, and here we applied the 600 here. How does that change the problem? Well, in one case it changed it a lot, in another case it didn't change it at all. For example, this 900 is a pushing force, but it's applied at joint F. You can apply it as a pulling force without changing anything. The resultants for the reactions are going to be the same, and the forces in these members are going to be the same as they were in either case. However, over here we can, by observation, see that by looking at joint B, this is a zero force member. However, if you pull it down from here, because these guys are lined up, this one has to be 600 in tension. So clearly those are not going to be the same with those forces applied at different spots. The same thing here. If I apply this force P here, I can see that this is a zero force member. However, if I apply the force here, I beg your pardon, this one is equal to P2 going up. In other words, it is going to be P2 in compression. However, if I apply the P2 over here, then you can see that this is now, by looking at this joint, this is a zero force member. So it changes the problem quite a bit. All right, and then the last one is just this one. We've talked briefly about this one before or already, but in this case, if I'm pulling down here with a 25 kilonewton force, what is this one? Well, it should be, if that's pulling down, these two are lined up, this one has to be 25 in tension. So that'd be 25 kilonewtons tension. However, if I push down here with that same 25 kilonewtons, this one here, by virtue of this joint, becomes 0. So that can help you a lot when you're doing truss analysis, is just to recognize the concurrent members here, and or concurrent forces, as well as zero force members when you look at those. Well, I just want to walk through a couple of problems with you very briefly, in that how you approach them. How do you approach the problem? So I'm not going to solve these. The answers here are given. I just want to help you understand how you go about doing this. So let's say we have this truss, and we want to find the force in BD. Well, you may be tempted to go right to point B and try to solve things. However, there are 4 unknowns, and that's pretty hard to understand and pretty hard to evaluate those 4 unknowns when you just go straight to point B. So what I'm going to do, instead of try to do that, I'm going to go to point A, then go to point E, and then go to point B, something like that. All right, so I'm going to find the reactions first. So in this case, I have a theta, and I can sum the moments about. Let's draw the reactions here. I'm going to have an AY, an AX, and a CY. And when I sum the moments about A, I can find CY. Sum the forces in the Y, I can find AY. Sum the forces in 0, I can find AX is equal to 0. So interesting. AX is equal to 0 in this case. So let's move to joint A. I'm going to draw the reaction, AY. I've already got an answer for that. There is no AX here. So I'm going to expect that this joint, which is AE, is going to be in compression. Why do I know that? Well, because, let's draw the other force here. I'm going to say that this one is going to be AB. How do I know AE is in compression, pushing down? Well, if I know this one is pushing up, there has to be some component pushing back down, because AB is only going in the X direction. The only component that could be available to push back down would be this AE sine theta. This is going to be the angle theta. So what have I got? AY minus AE sine theta is pushing down, and I can solve for AE. Some of the forces in the X, and I can solve for AB. So now that I have AE, it is a compression member pushing in. Let's move to joint E. If it is compression on one end, or at one point is off, it's got to be compression in this one as well. Now let's look at what we've got. I've got EB and ED. How do I know they're going in that direction? Well, EB has to be going this way because it has to counteract the Y component of AE. CAE has an X component. This one has no X component. Therefore, ED has to be going in this direction, and you can resolve that. Once you find EB as a tension member, you move it down to point B. You know that AB is already a tension member. I'm going to assume those two are tension members. I have this 800. I can solve these guys and understand that BC is equal to 0, and BD was what we were looking for. Okay, well, I hope that makes sense. You don't have to move on to the rest of it if you got to what the problem was looking for. In this case, I also solved for CD by just summing the forces in the Y. CY here had a value, and you can find that that was also CD is equal to 400. All right, the last one I want to walk through here is just this one. Again, we're not going to put any numbers here. All I'm just trying to say, let's say that the problem asks for FE. What is happening in this member? Well, it's difficult to start here. No forces are applied. You could find the reactions, which is a good approach. But another way of doing it is to start here, find out what is going on in DE and DC, and you can do that with one picture or with one free body diagram. Then recognize that CE right here, by virtue of this joint, is a zero force member. So if that is 0, then you can move with this information here, knowing what DE is. So DE is going to be pulling back here. Knowing this is 0, you should be able to solve for these two as well. And you should be able to solve then for DE, or sorry, FE, with just that picture after you start here. So anyway, there's some approaches that you might try. Look for obvious zero force members and concurrent members, and that can help you make some progress.